So the video I was showing you guys just now is about the MASER. Someone here? Yep. Okay. So it's about the in the video it's about the diamond MASER, and what we will learn, we will finish this chapter very soon. So after that we will go to talk about the MASER, but for us we will learn a more primitive and perhaps easier version of the MASER, which is the ammonia MASER, right? So ammonia is one of the main contents of human waste, so it might smell like the toilet, but if you have joined like the first aid training and things like that, I remember learning about the ammonia salts. So the ammonia salt is used to wake up a person who has fainted because of the sharp smell and the reaction to the body and things like that. So yes, ammonia. So we'll learn all about that later, but let us finish off a couple of things about the Stern-Gerlach experiment. So wait, how's my sound? Too loud? Too soft? Too loud? Okay, test. I think everything is fine. Okay, so yeah, so so last week we covered most of the basic concept about the Stern-Gerlach experiment already, and there's many more aspects about the Stern-Gerlach experiment and which we will learn more and more later. Okay, so we will come back to a few concepts about this once we learn a few more methods, because we haven't learned that yet. So we will finish some basic concepts for now, and then we will come back to this again later. But for now, remember last week we were talking about the given the basic Stern-Gerlach setup, right? We are detecting the spin of silver atoms. So for this experiment we're talking about silver atoms, right? And the Stern-Gerlach experiment shows us that the spin is quantized, is either up or down. Okay, either up or down. Then using this setup we can sort of do a few kinds of manipulations to it. So firstly is the Stern-Gerlach magnet, right? So the Stern-Gerlach magnet, we've been calling this sigma z. Okay, so sigma z is the one that splits the states or spin up and spin down. Okay, and the Stern-Gerlach magnet is given by 100 minus 1. Okay, so we have been playing with this operator already. So the main reason why we want to learn the Stern-Gerlach experiment is to get used to the language of operator, because we know that for student learning quantum mechanics for the first time, Hilbert space, everything is very abstract. So we want to relate this to experiment, but we haven't learned everything yet, so we cannot so we will learn some basic things first. So these are the few operators that we have been covering on the since last week, right? So this is the Stern-Gerlach magnet. It will measure whether the state is up or down with a certain probability. We have learned how to get the probabilities and the expectation values. And then we introduced another thing called the selector. Selector is basically the Stern-Gerlach magnet, but you discard one of the outputs and you keep the other one. So for any arbitrary superposition, a plus selector will only keep the up state. Whatever is down, they throw away, right? So you got this, and it is represented by this operator. So in matrix form you can write it like this. In the ket bra form you can write it like this. Okay, so same story for the down selector. The down selector only selects the down states. Then in matrix form you can write it in this way, 0001, or in the ket bra form you can write it in this way, right? So hopefully everyone by now is starting to get used to manipulating the bra-ket, right? And I hope you agree with me, it feels like playing Tetris. So if you kind of get that feeling, then you can kind of get the essence of the bra-ket notation already. Then you're on the right track. Okay, so that is the selector. Okay, then for today I will introduce to you another device which we call a flipper. So flipper, from the word you can guess, it will flip the state, right? So what it does is it flips. If a atom in state up enters the flipper device, it will come to state down, and then if a down state comes into the thing, it will become the up state. Okay, so the way it does is by using a special arrangement of magnetic fields. So so we don't need to know about the details for now, because now we are just learning how to play with the operators. The experimental technique to achieve this is another problem, which we will briefly discuss later. So for the moment, I would say that it can be achieved in experiment using a certain configuration of magnetic field. Of magnetic field. So let's keep it like this for now. Okay, so we can do this, right? So in other words, I have a device that is entering a flipper, and the down state comes in, right? So if a up state, if a down state enters the flipper, it turns into an up state. So it's like having some kind of magnetic field that can rotate the thing and make it become up. So the thing that is going up, the same magnetic field can rotate it and make it come down. Okay, so that is the flipper operation. So the operator, the flipper is represented by the operator, right? So the operator corresponding to this flipper is, I want to find a matrix that turns 1 0 into 0 1, and then something with 0 1 turns into 1 0, right? So the flipper is represented by an operator. That is given by f, which is 0 1 minus 1 0. Okay, so in ket bra form, right? So in ket bra form, this is up down, and then this is down up with a minus sign. Okay, so we can see how this works. So if I act the flipper on the up state, right, I can use the bra-ket form or the ket bra form. Hang on, down up. Wait, this is oh, correct, right? Yeah, this is down up. Yeah, so now we can see how it works. Up acting on the down, plus down acting on the up. Wait, why am I confusing myself? Acting on the up. So this is minus sign, yeah. Right? Then I want to act this on the up state, then I get negative down. Right? So you can write this as matrix form as well, 0 1 minus 1 0, right? Acting on the up state. So 0 0, right? And then I got minus 1 0, so 0 minus 1, right? Which is the negative down state. So now, so this is how we can get the correct representation. Okay, so there's an extra minus sign here, but it doesn't matter, because remember that the overall factor usually doesn't matter, even if there's a minus sign. Okay, but let us complete our picture by acting this on the down state. So on the down state, how does it look like? Well, this is my flipper operator, up, down, minus, down, up. And I want to act this on the down state, right? So this times this, the down state gone, then it's too bright. Then this times the down state, you will end up with the up, right? So this times this, it will times together, it will disappear and left behind with the up state, right? You can, or if you are not comfortable with, if you are still not comfortable with doing this, then we can always do the matrix form, 0 1. So what we find is 1, and then you got a 0, which is just the up state again, right? So this is the flipper operation, right? It acts on the up state to give you the down, and the down state to give you an up. So an arbitrary state, right? So let's say my state is some arbitrary superposition of up and down. Okay, so some quantum superposition state enters the flipper. Basically, it will just interchange the two of them, right? But now we got a phase factor. So what we have here, it becomes F acting on this state is, you can do it in the matrix way, right? You can do it in the matrix way, but I think the matrix way everyone is familiar. So let us practice the operator way. So it's the ket bra up down minus down up, right? And then I want to act on this state. So for the first term, right, the up times this, I got a minus a down, right? And then the other term is 0, but this times this will get 0, this times this, the down will disappear, and I've got a b up, right? So when you act on an arbitrary state, this is what you will get. Okay, so this is pretty straightforward. Okay, so yeah, that is the flipper operation. Okay, so yeah, no question, right? This is pretty direct and probably easier than the selector and the sigma z operator. But why do we want to introduce something like this at this stage is because right now I can already give you a preview of advanced research that is going on right now. Because we have a few things already, right? What we have here is the sigma z operator, we have the selectors plus and minus, and we have the flipper. So these are devices that can manipulate the state of an atom up or down. In fact, if you imagine like each of them is some device that you can build, it's almost like Lego, right? You got this machine, you got this device, you got this device. Then you can connect this device one after another. And this brings us to successive Stern-Gerlach operations. Although in the context of Stern-Gerlach operations, we seldom use this word, but if you do this right, this is what people today is doing something similar, and we call this quantum circuits. It's almost like quantum circuits, because for quantum circuit is manipulating spin, but they do not use the silver atoms, not so much nowadays. Okay, so this is the successive Stern-Gerlach operation. So the Stern-Gerlach experiment was first done in the 1920s, and is to demonstrate the quantization. But the similar concept, although people no longer use ammonia, they're doing quantum circuits, and quantum circuits is something that is used for many things in research. I have mentioned a few of them already, probably in previous classes, but it is used for quantum computation, and then quantum cryptography, and many other current research that is happening today. So so a lot of advanced research, but as you will see later, right, it's actually very simple. The basic premise is very simple. So what we're doing is that these are primitive. So what we are considering today are primitive versions of these concepts, the quantum computing, right? So let us see, right? So let us join some of these devices together. Let us start with this. What happens if I feed a quantum silver atom into the plus selector? So whatever state this is, it becomes a up state. But then if I connect this to a down selector, then what do you get? Nothing, right? Because this one discards anything that is in the down state, but this one discards anything in the up state. So basically you throw away everything, so nothing comes out, right? So nothing comes out. So if you want to write this in equations, right? So the main idea of quantum computing and cryptography, right? You have the experiment, but you also need to design the program, the algorithm. This is the software, and this is one way to connect the quantum software to quantum hardware. So this is the hardware, right? You can do this in the experiment, but in the software language, you need to represent in equation. So in equation, it looks like this. Okay, so after you pass through the S plus selector, what comes out is S plus acting on this, right? We do the matrix multiplication, and then after you pass through a S minus operator, so you got S minus operator multiply from the left. Okay, so you got this, right? And according to what we expect from experiment, you get a 0. So what does this mean? So this means, well, let's see, right? So for any state, for any state, well, S plus is the up operator acting on this, right? So this could be any arbitrary superposition, and then this one is the S minus. So S minus is the down, and then and then this whole thing is S plus times this. So it's up side, but this part is equals to 0, so you get 0 over here. Okay, and the main reason is, of course, as you can see, right, S plus times S minus is 0, right? Because we can just multiply directly. In other words, S minus S plus is 0 0 0 0 1 and then 1 0 0 0, right? So if you multiply everything, you just get a 0 matrix. So this is a nothing operator. So this is a simple quantum circuit, actually a very useless quantum circuit, because you put in a state and then nothing comes out, right? Or maybe not is used for something. It definitely has some use, because you want to kill off certain states for certain quantum computing operations. Okay, so the sequence of experiment can be represented by operators multiplied in the reverse direction. Okay, so yeah, any question? No, 0 means nothing. Yeah, so 0 means nothing. Nothing comes up. Because you throw away the up state, right? So this one is a filter, and then remember the selector, if you keep the up atoms and then the down atoms you throw away, so you no more. And then the up atom, you go through the minus filter, you throw away all the up state, so you throw away everything, no more atoms. So it's not to say it doesn't spin, but like literally no atom comes out of this. Okay, so that is what it means over here. Yeah, let me turn on the lights to make it a constant light source. Where the atom go? Rubbish bin, you discard, right? So it's an experiment. You just throw away, like, yeah, you can just imagine like throw away in the rubbish bin or some container that you don't use, because what you focus on is the output of the device, right? Whatever it is, you throw away. So the up spin throw away to some the up spin throw away to some dust, yeah, rubbish bin, whatever. Okay, so it's not so important. Now let's talk about another circuit. Okay, so let's see what happens if I take a silver atom beam, whatever the state is, right, and I pass it through a flipper. Okay, and then if I pass it through a flipper, and then after the flipper I put the plus selector, and then I flip this back. Okay, so what's going to happen here? All right, so this is now like more like, it's really becoming more, not just Tetris now, it's like more like the puzzle things where all kinds of games you can play with this type of situation. So if I feed in the up state, after I flip this, flipping this will become down, right? So become down, and then I get the plus selector, so it discards the down state, so nothing comes out, so nothing to flip, then everything gets discarded. But if I feed this the down state, then what's going to happen here? So if I feed this the down state, then if I flip this, this becomes the up state, right? And then I have the plus selector. So plus selector, I chose the plus, yes. Then it's still up. And then I flip this back, and then I get the down. Okay. So notice what is happening here. If you just look at this as one overall device, right? So what is happening here is the up state gone, nothing. The down state comes out as a down state. So this is equivalent to a down selector. Okay, can you see? So we can try to represent this mathematically, right? So for any state, right? So if I pass through the flipper, so what comes out is going to be the F acted on this state, right? And then I pass through the S plus selector. So it's S plus acting on F on the previous state, right? And then I pass through another flipper again. So it's F, S plus F acting on the down state. So let's check what does this state look like, right? So the flipper was, I forgot what's the flipper like. The flipper was this, right? So let's check this operator. F, S plus F is equals to, the flipper was up, down, minus. So up, down, minus, down, up, right? And then acting on the S plus selector. So S plus selector is up, up, right? And then act on another flipper, so which is up, down, minus, down, up. You can also do the matrix multiplication, but I guess we want to practice using the cat bra, right? So down, up. Let us multiply this way. You can multiply to the left if you want, right? But usually I'm used to multiplying to the right. So up, up, this becomes up, down, and then this one will become 0, right? So now this one act on this. So this times this you get 0. So this times this you get 0, and then this times this you get down, down, right? So we've realized that this is F, this, okay? So we've concluded that this is S minus. So we have proven that F, S plus times F is negative S minus, okay? So again, as before, usually overall sign does not make a big difference. So I shouldn't say not important, because there are situations it's not, but yeah, let's put it as not important for now. So because the effect is equivalent to having a down flipper, right? So what comes out, if you actually do the calculation, it should be an extra minus sign at the back. But the main point is, because we are trying to connect this to experiments, sometimes mathematics got some extra symbols and extra negative signs. But in the experiment, yes, if you put an up atom through it, nothing comes out. If you put a down atom through it, the down atom continues to pass through. Okay, so this is the equivalent, another equivalent circuit for the S minus, right? So in quantum computing, this is the kind of calculations you always do. You join many devices, then you realize that instead of doing this, you might as well just, instead of building 3 successive devices, you can just replace it by just another S minus device that is doing the equivalent things to this thing over here, right? So that is kind of like what people are doing a lot in quantum computing. You know, so I think if you read those online stuff that sometimes I share in the teams, right? People talk about quantum computers and saying using computers to compute calculation kind of thing, well, now you know what is happening here, right? It's this kind of operation. Because computer is doing what? Computer is taking everything, all the data in computers is represented by binary digits, right? Zeros and ones. And then the data is all is 0, 1, 0, 0, all the sequence of zeros and ones, right? And if you want to do a calculation, they manipulate the zeros and ones, and then you see what the output comes out, right? It's binary digits. So in quantum computing, this is the 0, and this is the 1. So you can do this on, you can imagine doing this operation on all kinds of data, then you can build a program based on this, because a program is manipulating zeros and ones. Okay, so that is the essence and basic idea of quantum computing. Okay, any questions so far? Very interesting, right? I hope. Like the polarizing experiment. Which polarizing experiment? Oh, the like the photons, right? Yeah. Yes. Kind of. Yes. So can down up be F? Yes. So if you change the minus sign, yes, because the effect will still be the same. Yeah. But it will introduce the phase, right? So the extra phase actually, why I say not important for now, this extra minus sign that pop up here and there, or like Zuri was saying, another F. So let's call this F prime, right? So F prime is where the, is that what you're writing? Yeah, the minus sign is with the up, right? So it's the down plus, down, up, right? So it's equivalent. But there's an extra phase. So this is why I say for now, because sometimes in quantum computing, in more advanced and more sophisticated manipulation, more precise manipulation, you can use the phase to do some operations as well. So so that is where it becomes important. But for now, we are just learning the basic things. Then yes, we just need to care what goes in and what comes out. Then for that, then yes, it's equivalent. Okay. But one more thing, when we talk about the operations, right, is that partly related to the overall factor is the issue of normalization. Okay, so what happens here is that yeah, up, down, up, yes, so it's still the same thing. Actually, up, down, up is my original F, right? So this is the negative F of the same thing. Okay, so this is about what I meant about quantum computing, right? Yeah. So so even just at this level, right? Now that you're just started this course on quantum mechanics, you can already kind of get a taste of what people are doing when we're doing quantum computing, right? Both the theory side and the experiment side. So, and also I show you the video, you know, what the lab looks like. In the previous video also, the quantum computing lab looks the similar way. And the best, this is why, another thing why quantum mechanics is an interesting field of research is theoretical and experimental side are at the same level as each other, right? So new theory can be immediately tested in experiment, and new experimental discovery can be immediately studied by theory. So this is quite a rare chance because it doesn't always happen. Imagine like my research field, the theory is too far ahead of experiment, right? Einstein predicted black hole like 100 years ago, but only last year or 2-3 years ago, we took a picture of it. And like there's a very big discrepancy between theory and experiment. So the issue of normalization, right, is that because the operator the state did not really normalize, is not really normalized after coming out. So after passing through the sigma z, right, s plus minus, or the flipper, the state may not be normalized. Okay, so let's take an example, right? So if I take an arbitrary state, A up plus B down, right? So if I want to be normalized, this is psi is normalized. If this is normalized, it means that the modulus A square plus modulus B square is equals to 1. Okay, so if this is normalized. But what if I pass this through a selector? Okay, so if I take this state, right, and then I pass through the S plus selector, what comes out? So what happens is, well, my state is here, and then I pass through my S plus selector, so I got S plus the state, and of course the S plus is the up arrow, and then I multiply it by A up B down, and then it kills off the down state. So what I have here is the up state left behind, right? So the output is just A up, right? And this is not normalized because the output is not normalized, because you can calculate the length is less than 1 because I got this, right? Output is not normalized. Remember what I mean when we say normalized, because normalized means you calculate what is this value. Okay, so yeah, we flip this. Okay, so we flip this, we got A, not flip, but the bra, right? We dagger this, and then times A up, so we got A square, right? So this is less than or equals to 1, right? So it's only normalized if B is equal to 0. Okay, so that means generally speaking the output is not normalized, so we need to fix the normalization. That means we fix it by dividing by the norm to make sure it's equals to 1, right? So this is not equals to 1, so we need to make sure it's equals to 1, so we fix it by dividing the state with its norm. So this is what we call the normalization procedure. Okay, so we divide by the state with its norm. That means we create a new and improved output state by taking the original state and divide by the norm. Right, so what was this? This was A up, right? And then this one was this one is just the absolute value of A squared, the square root, so you got A over A, and then this is the up state. Okay, so this was what we did last time at the end of previous class, where I was telling you that this is not equals to 1, but is in general is EI 5, right? The modulus is 1, the length of this part is 1, but whatever this is, this will ensure that the norm is 1, so that the norm is psi out. The normalized version is just going to be A bar over modulus A, dagger, so becomes this, and then before the dagger it becomes this, so you got A bar A over A square, up. So this is 1, this and this are the same thing, so they cancel and they are equals to 1. So now is normalized. So if you encounter a state that is not normalized, it's still a valid state, but the probability may not sum to 1. Okay, so that is the conclusion that we have here. Should I write it down? Yeah, let's write it down. So in general, generally, an unnormalized may still be a valid physical state, but the probabilities do not sum to 1, right? Because they do not sum to 1 because it's the overall thing do not sum to 1. So we need to normalize to get the correct probabilities. So this is one of the consequences of the normalization of the state. Okay. Correct. If psi is A up, then no need to normalize. This is what we mean that where was it? Yeah, it's only already normalized if B is 0. So if B is 0, it's just A up. And A, if it's just A up, the original normalization means A equals to 1. Then yes, then it's normalized. So yeah, so if A up equals to 1, then it's already normalized. Okay. Yeah, so that we were talking about the same thing. So yes. Okay, so let me give you an example of an unnormalized state. Okay, so this is example 2.1.2. Okay, so let's give an state from the lecture notes, like 5 up and 7 down. So from here, both of these are quite a large number, so we can expect that this is not normalized, right? So because if it's not normalized, then we cannot calculate the probabilities correctly. They will not sum to 1, right? This square plus this square, you get a huge number. But we need to normalize this by finding the norm first. So by finding the norm, is just 5 squared plus 7 squared, right? So you get 25 plus 49. This is 74. Okay. So to the normalized version of this state is, well, we divide this by the norm. So we do this, right? So it's basically 5 up, 7 down, divided by the square root of 74. Okay. So yeah, so it looks like this: 74 square root 5 up plus 7 down. Okay, so this is the normalized state. Once you normalize, then only you can calculate the probability. So let's check the probabilities. Okay, so let's check the probabilities. What is the probability of observing 1 for this state? So let's do, yeah, as usual, we do this, right? So we close the value that we want, and then we take the modulus square. Okay, so that means it's equals to taking the up state, and then we close this on 1 over 74, 5 up, 7 down, right? So this times the back will get you 0. This times this, it will give you 5 over square root 74, but absolute square. So I got 25 over 74. Okay, and then you do the same thing for the down state. You act on the down of the normalized state, right? And then yeah, you do this, then 1 over 74, acting on 5 up plus 7 down. So this one times this, you get 0. This one times this is 7 over 74, so it's 49 over 74. Then you can check the sum of probabilities. The probability of up plus the probability of down is 5 over 74, 25 over 74 plus 49 over 74, and of course you get 1. So this is how you can get the correct probability. So this is kind of important, right? Because sometimes after you feed your state through a quantum circuit, what comes out might be some state that is not normalized, then the probability that you calculate might be wrong. So that is this is one of the things that you need to be careful about. Okay? Yeah, so any question? Okay, So I think that's all the basic things that I wanted to cover about the Stern-Gerlach experiment for now. We will come back to this experiment again in a later chapter, but we still have a few more extra things to learn, right? So we still need to learn a few things from chapters 3, 4, and 5 first, but now we should probably move on to another two-state system. Magic. You mean this is magic? Kind of, right? So, yeah. I forgot to mention that another comment about quantum computing is that, yeah, quantum computing is, because in quantum, in classical computing, right? Right, so the data is like a sequence of zeros and 1, right? So data can be like 0 1 0 0 1 1 0 0 dot dot dot. Okay, so and then you can so what people do is they in the classical computing, they use this what we call the logic gates. So your x is like 0 1 0 0 1 1 0 0, and then they pass through some logic gates, and then you get the output, right? So that is the classical computing using 0 and 1. But then for quantum computing, your data is represented by a quantum state. Okay, so why is quantum computing very interesting now? Because quantum computing can be in superposition, because you can do this, right? So when you pass something through a logic gate, not only you act on something like this, but you act on these two superposition at the same time. So it feels like your computation power is double, because you not only you got this state, but you can do computations on a superposition of state at the same time, right? And then what we do is, yeah, your state is like how do I write this? I haven't told you about the tensor product yet. 0 1 0 0 1 1 0 0 is basically like 0 1 0 0 1 1 0 0, right? So you all this you pass through the Stern-Gerlach, or the what we learn as the Stern-Gerlach experiment, but you can do this, you can do this, you can do whatever things, and then you get the output, right? And then you measure the output. So that is almost like, yeah, so it's the same principle, but you can do it on a superposition of states. For normal computers, like all the computers that we're using now is just classical computer, and it's discrete, right? It's either 0 or 1, and it's fixed. Okay, it's always 0 or it's always 1. Classical, right? Like the cat is either dead or cat is definitely alive, that kind of thing. But for quantum computing, you do the operation on superposition of states, and it's kind of expand the possibilities of computation, and this is why this is a very hot topic of research nowadays. So yeah, it's cool, right? Definitely, and it's almost like magic, like you said. Why your brain got PTSD? Did you learn about computing before? What is that superposition? Oh, the superposition is like exactly what we are talking about, right? Our Stern-Gerlach experiment. See, so like for one of these, so for in this picture, I draw a single state, but you don't need to just put a single state inside. You can feed a superposition into the gate, and then you calculate the output, right? So you can do more complicated things like this. Okay, so yeah, like you're manipulating 0 on 1 to get 0 1 or some other more complicated combinations. So for the moment, we can imagine this as something similar to our Stern-Gerlach experiment. So that was the main essence of the quantum computing. Was there S? You mean in the last picture I drew? Or the selector? Yeah, I just put a random example. Selector, sigma plus, sigma minus, whatever. Anything lah. So it's just a preview lah, because by right you guys are not supposed to learn quantum computers yet. It's supposed to be some kind of graduate level course, but I thought it would be at least be interesting to show, because the basic concept have already been taught already in chapter 2. But for now, I guess, what time are we at now? So I guess I will talk a little bit about ammonia MASER before we take a break. Right, so I have shown you the video before we started the class. The video is using diamond. Now we're using ammonia. Okay, so the MASER that we are talking about is because it's MASER, and MASER means microwave amplification by stimulated emission of radiation. Right, so MASER. It is seldom used nowadays because nowadays people use laser, and laser is because instead of microwave we use optical light, so it's a more general case, so it's light and then the rest are the same. Right, so this is what we call laser. So for the first device, I think so lah. Is people started by focusing on microwave wavelength first, and then the people built more and more complicated and more advanced experiment that the photon that comes out doesn't necessarily have to be in the microwave range. It could be other range, right? It could be XR laser, optical light laser, infrared, and things like that. So generally speaking, we got a laser light, and now laser is almost everywhere in our daily life, right? So if you play the Blu-ray DVD, it's actually using the laser light to shine on the disc to read the data, right? Or in concert party, all the laser light show, that kind of thing. Or in experiment, you use laser to cut things, a very, very strong laser. So laser is very important. Okay, so we are actually learning the basic idea, the basic operation of the MASER, and what we want to learn is how to build a MASER. So the idea of how do we create this laser light or MASER light is actually a difficult experimental procedure. This is why this is modern technology, right? So it did not exist 100 years ago because technology is not advanced enough, because to achieve the MASER and laser is actually not very simple. Why is it not very simple? Because the idea of MASER and laser, right, is a source of coherent light. Let's say coherent light. Coherent light means all photons exactly the same wavelength. Okay, so that is not very easy to achieve, because normal light source, you get light, sure, fine, but it is always a mixture of different wavelengths, right? So it is, but if you want to have something exactly the same wavelength on the whole light, then that is not very easy. Okay, so this is the main experimental challenge on how do we get the laser light. So if having exactly the same wavelength, that means hc over lambda is hf. All photons have the same frequency. Here we will call this h bar omega, right? So that is the idea of the photon. So we want to create a source of photons, and I want all my photons to have the same frequency all the time. So that is the ammonia MASER. Okay, yeah, let's talk a bit more. So let's talk about the like I said, right, I want to make a MASER using ammonia molecules. So this is 2.2.1 ammonia molecule. Okay. So before we start building this device, let us understand the physics of the ammonia molecule first. So let's study an ammonia molecule in vacuum. Okay, so what does an ammonia molecule looks like? So ammonia is, in chemistry we call it NH4, right? NH3 is one nitrogen atom attached to 3 hydrogen atoms. Okay, so it has two possible states. Yeah, so two possible states. Let me try to draw it. The nitrogen atom and is attached to 3 hydrogen atoms. Something like this. Okay, so it's very ugly. I kind of want to draw it again. NH3 smell very bad. Yeah, that's why Zuru was saying it's like a toilet. So this one very ugly. I'm not satisfied with this picture. Yeah, so ammonia smells very bad because one of the components of urine is ammonia, right? So it has a very sharp and pungent smell. So yeah, let's try to draw it again. So yeah, this is at the back. So this is my ammonia molecule. Okay, now we haven't learned fully a lot about quantum mechanics or chemistry, but what we do know is, well, I do say that nitrogen has a higher atomic number. Am I right? So the nucleus of the nitrogen atom has more protons. This is only 1 proton each. Okay, so 1 proton each, because so N has more protons in the nucleus. Right, so that means H only has 1 proton each. Remember, protons are positive charges, so the electrons, right, will obviously be more attracted to the strongly charged protons in the nitrogen atom. So electrons are more attracted towards the nitrogen part. Okay, so electrons are more concentrated near the nitrogen part of the atom. So this part will be lacking of electrons. Then I got 3 hydrogen atoms which are positively charged. Nucleus, 3 hydrogen nucleus are positively charged. Most of the electrons are attracted up here. So what is going to happen is there's going to be a net negative charge on the top part, and there's going to be a net positive charge on the bottom part. So when something has more, when I have a overall the molecule itself is neutral, but if you zoom into the molecule, right, most of the negative charges are near the nitrogen part, and most of the positive charges are due to the hydrogen part downstairs. So that will create a dipole moment, right? So this creates an electric dipole. Electric dipole. On the molecule. Okay, so dipole is well, the dipole, we define the dipole by a vector that is pointing from the negative side to the positive side, right? And we call this the P, the dipole moment. Okay, so we did learn about the dipole moment when we were doing the electromagnetism course, but we are talking about different aspects to it. But the main point for this is this dipole moment is a quantum state, right? So this is the electric version of the up and down states, right? Because this one was the magnetic dipole moment. So when we were talking about the Stern-Gerlach experiment, right, the silver atoms can have spin up or spin down. That was when we were studying the magnetic dipole moment. But for the ammonia molecule, this is because of the electric charges, so we got the electric dipole moment. So it is also two possible states, up or down. Okay, so that means I have two possible states of the nitrogen atom. So let me call this state, I shall call this state number 1. Right, so my dipole moment is pointing down, so I will call this state 1. And then the other way around, so the other orientation is like this. Right, so my dipole moment is pointing this way, and this is the second state. Okay, so I have two possible states here, and this is still two states, so I can write this as my usual column vector 1 0, or I can write this as 0 1. It's perfectly fine. This is the basis of my Hilbert space. Okay, so generally speaking, an arbitrary state will be the superposition of these two states. Is in general, I got some coefficient times state 1 plus some coefficient times state 2, or you can write this as C1 C2. Okay, so this is the system that we are about to solve, and I think probably now will be I'll take a break soon, and once we come back we will start to consider this. But I mentioned this for now. Notice that until now, right, we haven't actually solved the Schrödinger equation yet. For the Stern-Gerlach experiment, we are just learning how to play with the operators. For now, we really want to solve the Schrödinger equation. So after this, we will continue this by solving the Schrödinger equation to describe the behavior of this ammonia molecule. We start with the ammonia molecule in vacuum. Okay, any questions before we break? Yes, I think in chemistry it's called the polar molecule, right? So polar molecule has a dipole moment. I think also water, for example, water is also polar, right? So if you can isolate a water H2O molecule and leave it in vacuum, it is going to have the similar behavior when we solve the Schrödinger equation. That's an interesting point. Yeah, polar molecules. So these are what we call the polar molecules. So maybe this is familiar to anyone who has been learning chemistry, but I have not touched any chemistry since high school, so I don't remember most of it. Yes, because the main idea is seven protons, but if it's neutral, right, I believe it's also seven electrons and 7 electrons for the hydrogen, so 10 electrons. So in total there are 10 electrons and 10 protons in this whole system, right? 10 electrons and 10 protons, but the 7 protons are concentrated here, so there's a strong attractive force to pull most of the electrons to clump around this area, right? And then the rest are left behind here. there's some slight net positive charge. So water pipe is not in vacuum lah, so I guess not. Well, in any case, before we drag too long, let us take the break, right? Let go everyone to take a break for 10 minutes, and for those I can continue answering questions here if you want. Yeah, the electron position, yes, that is what makes the polar molecule, right? So let's take the 10 minutes break. Stop the recording. We continue that on next week, but for now we shall continue the story of MASERs. Okay. Okay, let me get some more paper. What else to add? Did I forget anything? Yeah, I guess that's the main thing I want to discuss with you guys here. But we are talking about the ammonia MASER. Okay. In fact, not yet MASER. We just want to understand the ammonia molecule in vacuum first. And also, like Zuri said, it should work for any polar molecule as long as there's a dipole moment. So because what we are actually calculating, right, we say ammonia because that's what the experiment uses, but what we are actually studying is the dipole moment states. So whether or not it's nitrogen or some other molecule is still described by these two states. Okay, so but for this case is not the magnetic up and down state like just now, but we are considering the electric dipole moment. So this part is based on Feynman's lectures. So those of you who have read Feynman lecture may have recognized this. We will follow Feynman called this state number 1 and state number 2. Okay, and arbitrary state is this superposition. But what we want to do now is to see how the state evolve with time. So the evolution of state over time is determined by the Schrödinger equation. And so we haven't really used the Schrödinger equation yet until now. So the Schrödinger equation is like this. Right, so even in bra-ket form, the Schrödinger equation is much easier to remember, right, than when you did in modern physics. But so the Schrödinger equation depends on the Hamiltonian, right? So the Hamiltonian is an operator that appears in Schrödinger equation, so it's natural to expect it will control the physical behavior of the ammonia molecule. But since we also haven't really learned much about atomic physics or chemistry or things like that, then how do we know how to figure out the Hamiltonian? We try to use reasoning, right? So let's try to identify the formula for the Hamiltonian. Okay, so this is what we can do, right? And this is one of the advantages of quantum mechanics, is that you can still try to solve a system even we don't really understand everything about it, right? The Hamiltonian of the system is the energy operator. It is an operator that describes the energy of this complicated chemical molecule, right? It's a molecule, it's chemistry. So there's a lot of rules of chemistry that should be important, but we are actually ignoring it here, and we don't actually know the rules. But we can still identify the Hamiltonian. Okay, so that is kind of like, you know, knowing nothing but trying to do it anyway. This is what we are attempting to do. So so the natural thing for theoretical physicists at this point is to try to assume a simple configuration. So let's see what happens if it is diagonal. If it's a diagonal matrix, it's going to be easy to solve, right? So if this is the case, then can we do it? Theoretical mechanics. Oh, already mentioning Hamiltonian. I was expecting nearer to the end of the course. That means you already learned Lagrangian. So that's cool. So if it is diagonal, that means what? So this is a two-dimensional Hilbert space. So my Hamiltonian is a 2 by 2 matrix, so I got H11, H12, H21, H22, right? So if it's diagonal, then if H21 and H12 is 0, then what happens to my Schrodinger equation? So my Schrodinger equation, right, is that remember that my psi is C1 and C2. So my IH bar d dt psi equals to H psi can be written as in column vector form dC1 dt dC2 dt, right? And if this is diagonal, then I got H11 0 0 H22, then this is C1 C2. Okay, so if you work out the matrix, right, this is basically just two equations, dC1 dt, and is equals to H11 C1, and the other equation is the derivative dC2 H22 C2, right? So basically you got these two pairs of equation. Okay, then the solutions is simply just, this is a simple differential equation, right? So we assume there are constants. So another simple assumption. So if we assume they are constant, then we would have gotten a solution which is AE minus I H11 T over H bar, right? We just bring this over and integrate. Same story here. We bring this over and integrate BE minus IH22 T over H bar. Okay, so that means C1 only depends on this thing and C2 only depends on this thing. So we got this, the solution is just AE minus I H bar T H bar 1 0, and then BE minus I H22 T H bar 0 1. Okay, so if my state started out in this form, then it will continue be like this. But if my state started out in this form, it will remain at this state. There is no mixture. It will not change between the two, right? So the conclusion that we find is that if diagonal, right, if my Hamiltonian is diagonal, then the states 1 and states 2, right, remember this is 1 and 2, are stationary states. Would be, because I'm just saying if. Okay, so we are just understanding the consequences of these two elements, right? If these two terms are 0. So what is the lesson that we learned here? Well, these two are stationary states, but what are the values of this? Well, we can also reason out. This will correspond to the energy of state 1, and this will correspond to the energy of state 2, right? So if you apply this, right, so if I take the Hamiltonian 1, okay, if you work out the multiplication and everything, I will get H11 1, and if you work out the Hamiltonian 2, I get H22 2. So these are the energies of state 1, and H22 is the energy of state 2. Okay, so but what should actually be the energy? Again, we still like don't know all the chemistry and things like that, but what we do know is this reasoning. This is an ammonia in vacuum, right? So we are talking about ammonia molecule in vacuum, and gravity is negligible. So there should be no difference between up or down, right? So there should be no preference of up arrow, the dipole moment, or the down arrow for the dipole moment. Okay, so I'm saying that in vacuum, right, these two states should have the same energy. So they should have the same energy. Okay. Okay, and from this reasoning, right, like from knowing nothing, not knowing chemistry and not knowing more advanced theories of quantum physics, I can already try to figure out that, yeah, the diagonal elements have the same value and it should correspond to the same energy for these two states. Okay, so we have gotten this. And then how about the off diagonal terms? So we are saying this is the situation where if is diagonal. We only say if. It's just our suddenly we make this assumption out of nowhere. So if it's not diagonal, then this probably might be the case. So in general, if H is not diagonal, that means, you know, if the diagonal term 0 means it will give a stationary state, it will remain at this state. So if these two are off diagonal, that means that there is a tendency for the state to change from 1 to 2 and 2 back to 1. Then 1 and 2 will not remain stationary. Okay, so the off diagonal terms correspond to the tendency of the atom to change states. Right? So these are the off diagonal terms, the H21 and H12. Now, so we make another assumption, right? Still knowing nothing much. These are all just purely out of reasonable assumptions. We shall let H21 and H12 be the same constant, and I will call this negative A. So this will ensure, this will give a Hermitian Hamiltonian for A real. Okay, so that means our Hamiltonian is now just by reasoning out of nowhere, you know, we can already guess a Hamiltonian that is generally looks like this. Okay, so this is the Hamiltonian of the system. Page 5, 6, page 7, page 8. Okay, does anyone have any question or any disagreement? If you are a bit confused by this, I think it's natural because we are trying to guess a Hamiltonian out of nowhere. So, but if we don't do this, then we can't go any further, right? So this is a common procedure in theoretical physics. Just by some reasonable assumption, you try to write down a reasonable form of the Hamiltonian. Oh, okay, so you will learn it in the future lah. So yeah, it's probably like you need to learn like a few more things first, Lagrangian first, then Hamiltonian. Okay, diagonal. Okay, diagonal means the diagonal means the matrix only got M1. So diagonal means everything everything other than these parts are 0. Right, so everybody here are 0. Okay, so diagonal means only the diagonal terms are non-zero. Everything besides that are 0. That's a diagonal matrix. Okay. The ket is the initial state and bra is the final state. That's related to the transition amplitude. So I think that is let's say phi and psi, right? So this is what we call the transition amplitude. But I think do not let Feynman confuse you at the moment, because we will not talk about this a lot, but this is called the transition amplitude. So if the state is initially at phi, what is the probability that it will end up at psi? So the probability you calculate by doing this. Okay, we actually, the version that we do, right, is actually this, right? The state is some arbitrary state, but what in the end, what is the probability that we'll get this? So this is what we call the final state. Feynman do it in this way, but Feynman's viewpoint is slightly different from what we are doing now. Okay. Yeah. Any other question? Okay. Yeah. So I know, yes, theoretical mechanics is going to be a bit challenging, but towards the end, right, you realize that quantum mechanics and theoretical mechanics is actually not that different, because quantum mechanics we are using Hamiltonian, and it's because later in theoretical mechanics you learn a bit more about Hamiltonian, and then you realize that, oh, suddenly we use Hamiltonian in quantum mechanics, and the Schrödinger equation is actually came partially from the same Hamiltonian from the theoretical mechanics. So yeah. Okay. So now that we have kind of like sort of guessed the Hamiltonian, let's see whether this is correct. And of course it is correct, because we are teaching it from the textbook, right? Feynman is in Feynman's textbook, because eventually it turns out to be consistent with more advanced theories of chemistry and things like that. So let's look at the Schrödinger equation and try to solve it. Okay, so the Schrödinger equation in operator in ket bra form is this, right? But of my state is given by C1, C2. So I want to know how these two states change over time. So therefore, I write this in matrix form. So I h bar the derivative C1, C2. And then we have, by using reasoning, my Hamiltonian looks like this. And then I got C1, C2. Okay. So from this, I can split this into two equations, one for each row. So the first equation is IH bar dC1 dt is equal to this times this. So this is E0 C1 minus AC2. And then the second equation is dC2 dt is negative AC2, C1 plus E0 C2, right? So I got two equations over here, right? So when the off diagonal terms are non-zero, then C1 and C2 appear in the equation for C1 derivative, right? So this is what we call a coupled ODE. You guys have learned coupled ODE, right? By Lim Tao Shen. So this is a coupled first order ODE, right? So this is why you took the ODE course, right? You need to learn things like this. Even if you haven't learned, well, it's easy enough to just solve using the basic methods. So C1 and C2 are appearing together. So let's see what happens if I take equation 1 plus equation 2. So if I take equation 1 plus equation 2, then, well, this plus this, I got IH bar is the derivative. The derivative operation is linear. Okay, so I got this plus this. And then let's see, E1, E naught, E naught, C1 plus C2. Then this is minus A, C1 plus C2. So the C1 and C2 appear together. So I can treat this as a independent variable by itself, right? So notice that we got the differential equation for C1 plus C2. So we can actually solve this. This is actually E0 minus A, C1 plus C2. So in other words, d dt, C1 plus C2 is minus I over H bar, E0 minus A, C1 plus C2. Okay. So we can solve this, right? This is a derivative of this is equals to constant time derivative of this. So the solution is general solution. I'm running out of ink. Hang on. So the general solution is the exponential, right? So it's C1 plus C2 is constant, right? And then I got exponential of this. So minus I E0 minus A T over H bar. Okay, so this is my solution for C1, C2. Clear so far? A little bit. Yeah, actually quantum mechanics is extremely difficult. It is because as you can see in this course, right, QM1, even by the simplest molecule, just hydrogen atom, we're going to spend probably one whole week solving the hydrogen atom. And then the chemistry people, imagine they're doing some complicated molecules. So their Schrodinger equation is going to be way worse than what physics deal with. So in that sense, you know, chemistry is actually more challenging than physics, especially when you deal with chemistry of all these things. So yeah, so where were we? So we have solved C1 plus C2 already, right? But notice that we can also take equation 1 minus equation 2, right? So similarly, take equation 1 minus equation 2, and we got another solution. I h bar d dt C1 minus C2, right? And then so should I do all the steps? What time do we have? Yeah, just let's do all the steps. So I got E0 C1 minus C2 minus A minus A. So this minus this. So this minus this, but I want to keep C1 in front, so I pull out a negative sign. Okay? So to make sure that this, yeah, I'm skipping a few steps, so that's why you suddenly see this. But anyway, the method, the general idea is the same. I over H bar, I factorize C1 and C2, so I got E0 plus A C1 minus C2. So the general solution for this case is another constant, exponential I E0 plus A T over H bar. So I got another solution, right? So I got my solution in terms of the sum of C1, C2 and the difference of C1, C2. But I want to find the individual C1 and individual C2. So I need to take the difference of these two, right? So to recover C1 and C2 individually, right? So let's begin by, well, I take this plus this. Right, so if I take this plus this, then I got 2C1 and this, so it's basically this plus this. So it's A E I E0 minus A T over H bar plus B E minus I E0 plus A T over H bar. So finally I have found my solution for C1 at least. So my C1 solution is just a half of all this stuff here. Okay, so this is my C1. Then if you do the same method, right? If I take equation 3 minus equation 4, right? So I think, yeah, I will skip ahead because it's the same thing, so I don't want to waste time. You get the C2 solution. So the C2 solution is just a half of AE minus I, hang on, yeah, IE0 minus A T over H bar, and then got this time is a minus. Okay, so I can try to simplify a little bit. Let's see if I can simplify. Both of them has the factor. Simplify the solution. So both of them have the same exponential E0, right? Minus IE0t, minus IE0t, minus IE0t, minus IE0t. So they have the same exponential factor. So I can try to pull it up. So my C1, right? It was a half, and then I take out the exponential of IE0t over H bar, and then what is inside? So what is inside is A E IAT over H bar plus B minus IAT over H bar, and then C2 is taking out the factor, so half E minus IE0t over H bar, and then taking this out, so I am left with positive IAT over H bar minus BE minus IAT over H bar. Okay, so we have found the solution, right? So my state, how it changes over time, well, it was C1 over T state 1 plus C2T coefficient for the state 2. So my C1 is given here, my C2 is given here, and this is how it evolves, right? So this is a general solution. So the actual there's a constants A and B. So the constants A and B will be depending on the initial condition, right? Just like any ordinary differential equations, for the first order ODE you get constants, right? And this constant will come from the initial condition of the system. Determined by the initial condition of the molecule, right? So that means what we're talking about is what happens to the molecule at time 0. What is the state, or in other words, the state at t equals 0. So what time is it now? Okay, any question? So it's 10:50. Actually 10:50 is, yeah. I guess let's leave it for now. Its time is over, right? I better not start something else so that it will take up too much time and it will drag on for too long. But I guess this should be enough for everyone to digest, right? So this is the main procedure that we will spend the next class doing a little bit to explore a little bit further. So to summarize, right, without going to a new thing, I should probably just summarize at least, right? What we have found is this is the Schrödinger equation obeyed by an ammonia molecule or any polar molecule. So written in this basis, I have split my Schrödinger equation into two coupled first order ODEs, and using this trick I just want to solve for C1 and C2, right? So I do this manipulation. Basically at the end of the day I just want to get an answer for C1 and C2, and currently my answer depends on two constants. Is understandable because this constant depends on the state at time equals to 0. So when we continue in the next class, we will consider specific states so that I can figure out what is the correct A and B, and we can get the full solution to the final solution or the complete solution to the Schrödinger equation describing the ammonia molecule in vacuum. We are still just talking about just the molecule in vacuum by itself. Okay, so yeah, so I think that's about it for today. Any other question? If not, then let me stop the recording here. Okay.